Dear Mythagony Aunt, recently I carried out work on the circle with my top set Year 9 group. They're very bright and I don't think the activities I prepared were very inspirational. Can you suggest some exciting and unusual activities relating to pi? Because I don't have any in my portfolio. Thanks, Andrew Wilson.
Right, I need some parallel lines. Simon. Is it?
Nice.
Brilliant, thanks. You're probably wondering what I'm doing, throwing French sticks over my shoulders. Well, apparently in 1777, Georges-Louis Leclerc, Comte de Buffon, did this very experiment to estimate the value of pi. Imagine the scene. You've got French dignitaries, you've got servants running up and down picking up the sticks, and you've got French aristocrats looking and thinking, well, what on earth is Buffon up to? When Buffon did this experiment, he had squares. Now, as you can see, we've got parallel lines. What we need to do next is we need to count the number of sticks that either cross the line or touch the line. So let's do that now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now that's 11. I threw 20 sticks altogether, so we need to do a calculation putting those numbers into one of Buffon's formulae. So what I'm going to do is divide 20 by 11, and then I'm going to times that by 2. And I get an answer of 3.6. Well, actually, that's not very accurate for pi, because pi is 3.14 and lots of other places. So why haven't I got an accurate answer? Well, Buffon will have done this experiment many times, and the more times he did it, the more accurate his answer will have become. I expect the story's been somewhat embellished over the years, but students at Viner's school are going to try it out. Their starting point isn't quite so wacky though, because Steve Emerson, their teacher, has decided to use polygons as a way of estimating pi, and then they're going to do Buffon. Steve has invited us into his top set Year 9 group.
Now, I know somebody called Doris, and unfortunately, Doris didn't really take her teacher's word very seriously about pi and decided to set about doing an experiment to establish just how accurate her teacher was. And this is what she tried to do. She decided to find the centre of her square, and she measured the perimeter of the square. Now I want you to look at that square. Do you think that by measuring the perimeter of that square that is going to come anywhere close to the circumference of that circle? Good. I'm pleased to see no hands going up. Everything about the polygons was based on the idea of starting with a square, bisecting angles to create a shape which had twice as many sides, and then bisecting those angles, so going from 4-sided to 8-sided to 16-sided, so you have your geometric progression there.
Steve covered geometric progressions in the previous lesson.
What did Doris do to estimate the circumference of the circle using the octagon? Shannon?
Find out the perimeter of the octagon.
Yes, Shannon, she did. Excellent.
Steve uses this idea to demonstrate that by continuing to double the number of sides, the perimeter of the polygon approaches the circumference of the circle.
Do you think her estimate on the perimeter will get better or worse? Daniel, what do you think?
Better.
Put your hand up if you agree with Daniel. Excellent. I agree.
Steve gives them an activity involving 3 polygons. They only need a quarter of each shape to complete the activity. The polygons have 8, 16 and 32 sides. Each radial is equivalent to the radius of the circle. To measure the radials, Steve gives them a paper rule, specially scaled to suit this exercise, so the units don't matter.
In other words, if you put your paper ruler along any of the radials, it should be 0.5 units. Does it matter that we don't know what the units are? Yes, Charlotte?
Because the radius is always half of the diameter and the diameter's 1, it's always going to be 0.5.
So therefore it's going to be 0.5 whatever units. Absolutely right. Excellent. Thank you, Charlotte.
The reason Steve has constructed this activity with a diameter of 1 is because the students will get an estimate of pi by calculating the perimeter of each polygon. If d equals 1, then c equals pi.
How close to pi can we get?
Oh no, that one.
Okay, the actual circle and any of the other sides of the circle. And that's roughly a quarter of the diameter.
No, it's closer.
During the activity, the students discover that as the number of sides increase, their estimate of pi improves because the perimeter gets closer to the circumference of the circle.
So the further out you go, the better the estimate is of pi. Yeah. That's it.
Yeah, okay.
Steve gives them another formula for estimating pi.
I've put in the number 16, and it says a regular polygon with 16 sides and diameter 1 unit has perimeter equal to, and I'm going to click so that the formula shows 16. And 16 times this peculiar function called sine of 180 divided by 16 gives you something very, very familiar looking, doesn't it? I'm just going to try one more now. I'm going to put in 64. It's getting more convincing, isn't it? That's pretty close, 3.14.
Using this formula, they can see clearly that the value of pi improves as the number of sides increase. OK, Andrew, before Steve goes on to Buffon, here's another surprise connected to pi. Here we've got a circle with all the letters of the alphabet. Now I'm going to take off every letter that has a vertical line of symmetry. So A, H, I, M, O, T, U, V, W, X and Y. So what do we see? 3, 1, 4, 1, 6. The first 5 figures of pi. What a coincidence.
What we're going to do now is we're going to do an experiment which was in fact conducted by a rather curious character called Le Comte de Buffon, who was a mathematician that lived in the 18th century and who conducted this rather peculiar experiment. And what he did was he threw breadsticks onto a grid, and his servants were hurriedly recording which of the breadsticks crossed any of the lines on the grid.
Although Steve tells them Buffon's story, he leaves the purpose of the experiment a mystery.
You have in front of you a rather blank-looking piece of A3 paper. It has lines carefully spaced. You will find that the lines are exactly 1 cocktail stick apart.
Students get going on Steve's scaled-down version of the experiment. Working in groups of 3, one person stands with their back to the paper and throws 20 sticks. The others record how the sticks land on the grid. The experiment is repeated 20 times, and each time the roles of the groups are rotated to create more random data.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
They enter their results into a shared computer network. Steve is then able to draw on all their results and put them into Buffon's formula, which is 2n divided by c, to get an estimate of pi.
The totals of the number of times you've been doing this experiment is shown on the left-hand side. Okay? That is the number of sticks you've actually thrown. On the right-hand side is how many times you have been recording the lines being crossed. And the calculation, 2 times n divided by c, shown at the top there, is coming out at the moment at 3.6035 and so on. Okay? If you'd continued this experiment, what eventually do you think the result might have been? Jessie?
Pi.
What makes you think it would go towards pi, Jessie?
So far, it's been getting closer. The more times you do it, it's been getting close to the estimate of pi. So the more you do it, the closer it'll get.
Thank you, Jessie.
Steve shows them a simulation from the web, demonstrating what would happen if they could throw the sticks 100,000 times.
If you look at that running total at the top, it says number of tries, it's around 3,200. And look at the current estimate of pi, 3.22 something, 3.21, it keeps flickering around there. So the expectation is that it's going eventually to arrive at around what we take to be a reasonable estimate of pi. Now, isn't that strange?
I thought the Buffon experiment was good because you didn't expect the result that you got, and I never thought it would turn out with pi.
I thought that it was completely strange that the Buffon experiment would come up with pi, which has to do with circles, by just throwing random cocktail sticks at a grid.
I'm a bit puzzled myself as to why this works. I thought it'd be useful to look at some footage of the loaves being thrown in slow motion. Perhaps it might give us some clues. So here come the dancing loaves. Now, if I'm not mistaken, there are various rotations. This one is rolling like a cylinder. This one is rotating from end to end. And this one seems to be doing both. So, if rotations and hence circles are involved, could this explain why Buffon's experiment provides an approximation to pi? Perhaps your bright students could go and do an investigation on the web about Buffon's experiment. There's lots of stuff there, and I think they'll come up with some really interesting ideas. Perhaps they might even surprise you. Did you know that March the 14th is Pi Day? Perhaps you could have a circular party on the menu. Cross-curricular activities involving maybe the art department, perhaps some cookery, designing conical hats, creating pizzas and biscuits. You could even get the youngsters to go and invent some games based on the circle, and they could research some interesting facts about pi. Anyway, Andrew, thank you very much for your letter. I hope it's given you some interesting ideas that you can follow up with your students.